Hi again, we're back, and I'm here to talk about the binomial formula. And this is relating to the questions, among others, on the assignment 2 on page 261. They're all related to the binomial formula. What I'm going to do is I'm going to give you 3 bits of information. One is what the conditions are when you use the binomial formula. The next is what the binomial formula is and where it comes from. And then the third thing is just maybe an example of using it. Okay? So that's the plan. And hopefully that'll all go on one YouTube, but if it doesn't, I'll break it into 2 parts. So let's start with when do you use the binomial formula? Okay, so the binomial formula basically comes up when you're doing the same kind of experiment over and over again and you're counting the number of successes. Okay, so for example, a simple example is flipping a coin. If I flip a coin 20 times and I count the number of heads I'll get, that'll be a situation where I get the binomial formula. Will tell me about the probability of getting, say, exactly 3 heads. Okay, let me say that again, because there's an idea there. If I flip a coin 20 times and I ask myself, what is the probability I'll get exactly 3 heads? That's a situation where you get the binomial formula. That's sort of a classic type situation. So there's a few things that make the binomial formula happen. One is you're repeating the same experiment. Another is the individual experiments have 2 outcomes. So call them success and failure. And the outcome, and there's a fixed probability or fixed chance, call it P, of success. And by the way, we usually say 1 minus P, which we call Q, is the chance of failure. Okay? So that's another thing. And finally, the trials are independent. Oh, I guess that's not quite finally, because also you're counting success. So, by the way, what this trials are independent means is that the outcome of one coin toss doesn't influence the outcome of another coin toss. A lot of people have the misconception that that does happen, that somehow if you get 10 heads in a row, that means that you have more chance of getting a tail. Hopefully that's not the truth. Hopefully that 10 heads in a row means nothing about the next throw. If it does mean something about it, then we can't assume it's a binomial distribution. Okay? By the way, what this definitely means is that if you're drawing from a fixed population, one of 2 things has to be true to use a binomial formula. Either A, you're replacing in between draws, or B, the population is so large, really large population, so that it doesn't matter that you take one out. It doesn't really affect the next draw very much anyway. I mean, even in that case, it won't really be binomial, but it's okay to pretend it's binomial if it's a really large population. Generally, I think the definition of really large varies from place to place, but we can talk about that if we need to. I don't think we need to right now. Okay, so that's when you use the binomial formula. I'm just going to check my time to make sure. Okay, I've used 4 minutes. All right, so let's talk about what the binomial formula is and why it is. So this is when you use. Okay? That's when you use the binomial formula. So now, what is the binomial? So the binomial formula basically says, given n independent trials of the same experiment, with, let's say, fixed probability P of success and Q of failure, and those are the only two possibilities. The chance of getting exactly K successes is, so here comes the formula. Now it's going to use this, it's going to use this factorial term, k n factorial over k factorial times n minus k factorial times p to the k times q to the n minus k. That's as much math as you're ever going to see in this course. That's pretty mathy, isn't it? So I'll talk about what each of these terms is. I won't really talk in huge detail, but I will talk a bit about what each of those terms is. Okay. So let's say, just for the sake of let's say for the sake of argument that I have a box or an urn or something that has, let's say, 7 black marbles and, let's say, 3 red marbles. So if I mix them up and I draw out one marble, the probability that it'll be black, let's say, is 7 out of 10. And the probability that it'll be red, and let's call black success and red failure. Just, it doesn't have to be that way. You always get to define what you mean by success and what you mean by a failure and whatever. But actually, there is a rule for it. It's whatever you want to count. So if I'm saying black is a success, then what I'm saying is I want to count the blacks. So, and I'll say that Q, red, failure, is 3 out of 10. Okay? So what this formula is saying, basically, is that, well, let's imagine doing this a bunch of times. I'm going to pick a bunch of balls out. And every time that I draw a ball out, now I'm replacing in between. It's that you have to replace it because it's a small population. Every time I draw a ball out, there's a 7 out of 10 chance it's black. And every time I draw a ball out, there's a 3 out of 10 chance it's red. So if I was going to draw, let's say, 5 balls in a row, the chance of getting black, 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 red, red, black, black, so 5 balls in a row, right? The chance of getting black, 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 red, red would be 0.7 times 0.7 times 0.7, 1 for each of the blacks, and then times 0.3 times 0.3. So that would be the chance of getting black, 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 red, red. So that's this part. K in that case was 3, P was 0.7, and n minus k, 5 minus 3, was 2, and Q was 0.3. So I'm just going to write that down. This is my little example here. So I've got the formula there, but I'm doing a little example to try and explain how the formula works. So the chance of black, 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 red. So I'm going to do the red in red. Why not? is 0.7 times 0.7, 1 for each of the blacks. And remember, that's because I'm replacing them. That's why I use the 0.7 over and over instead of changing it, times 0.3 times 0.3, or what that equals, and I'll use the neutral blue color here for the answer, equals 0.7 to the 3 times 0.3 to the 2. So that is this part, 0.7 to 3.3 over 2. Okay? And check my time here. I'm a little over, so I'm going to continue this example on another video.